Welcome to week 3. This week we are going to be finishing up integrals and moving on to an introduction to differential equations. Now, just like last week, we're going to start with a couple review problems just to get you warmed up. So I want you to calculate the following integrals, and you have to figure out which method is going to work for them. Remember, this means that the x is cubed, not the cosine. Alright, go ahead, pause the video, take a moment, and make sure you remember how to do all of these. Alright, since this is review, I'm just going to go ahead and give you the answers so you can check yourself. So that one's pretty straightforward. This one, you use u substitution. And this one, I use the integral table. Okay, now that you're warmed up, let's move on to looking at integration by parts, the last integration method I want to make sure you know how to do. A lot of the integrals you can do by integration by parts. You can also do using integral tables. It's nice to be able to know where it comes from though. So let's look at it in the abstract form. So if we have an integral of the form u dv, this integral is u times v minus the integral of v du. So this is a way that you can do integrals if u substitution isn't working. For example, then you can check if integration by parts will work. So let's do an example. So we're looking at the integral x times e to the 3x dx. So u substitution doesn't work because if you assign u to be 3x, then your du would be 3 dx. We wouldn't know what to do with this x, so that's not going to work. So now we need to think about, when we're doing this formula, what should be our u and what should be our dv. We're looking for u, we're looking for our dv. So when you're choosing your u, you want to pick something that when you take its derivative, it's going to get simpler. So in this case, we would choose that to be x. And when you're choosing your dv, you can pick your thing that when you take its derivative or you integrate it, that it's not going to get simpler. Like you wouldn't want to pick e to the 3x to be your u, because when you take its derivative, you're still going to have an exponential, whereas when you take the derivative of x, it's going to get simpler. So we're going to assign our dv to be e to the 3x dx. Alright, now we need to figure out what du is, right? Because we need du right here. So du in this case is really simple, it's just dx, you know that. V, you have to take the integral of dv to figure out what v is. So we're taking the integral of e to the 3x dx. Now I'm going to start skipping my steps on my u substitution a little bit, but you can always pause the video if you need to work through it to convince yourself that what I'm doing is right. So when I take the integral of this with u substitution, I get 1/3 e to the 3x. Now, I'm not going to worry about putting plus c's because this is an intermediate step. And also, I would just point out, if you want to convince yourself that this integral I just took is correct, you can just think about taking the derivative. That would bring down the 3. The 3's would cancel out and you'd keep your exponential. Okay, so we have u and v, so we can do this part. And we have v and du, so we can do this part. Alright, so our integral is now u times v, so that's x over 3 e to the 3x, minus the integral of v du. So that's 1/3 e to the 3x dx. Okay, now what we're left with is, so this part is done, and this is an integral that we can just do by u substitution. Okay, now if I do use substitution on this one, I'm going to get another 1/3 that comes out. So I actually end up with a 1/9 e to the 3x, because we keep our exponential. Now that we're at the last step, I'm going to add the plus c. Okay, so I kind of rushed over how I do my use substitution, but remember, if you need to think through it more, you can pause the video and work through it yourself. But also, if it's still bothering you, please just let me know. Send me an email or make a comment in the problem solving discussion that you want me to slow down. But I hope as you do this more that with simple use substitutions that this will become more second nature to you. And sometimes when you do this, you end up with another integral that you have to do by integration by parts. So you do integration by parts repeatedly to make it work out. So I'm going to give you a few to try out. And I'm just going to give you a hint right now. This number 3 is one where the new integral you get is one that also requires you to do integration by parts. So this one, you basically have to do integration by parts twice. Alright, so pause the video and give it a go. Okay, so on this one, your simple function that's going to go away easily is your x. So you want to assign u to be x, just like in the example. So your dv equals sine x dx. Always make sure your dv has your dx in there. Okay, so what's our du? Our du is still simple, that's dx. And then your v, which is the integral of sine x dx, is minus cosine x. Alright, so let's plug this in. So we get u times v, so that's minus x cosine x, then minus our integral of v, which is minus cosine x dx. So then we have now here you want to be careful with your signs. If we go back and look at this, these minus signs cancel out. So we're just integrating cosine x, so we get plus sine x. And don't forget your plus c. Alright, done. And this is one that is in the integral table. Okay, next one. So now we have, well, our simple function that when we take its derivative it gets easier is 3x plus 2. So u equals 3x plus 2. And our dv then is e to the 4x dx. Okay, so du is just 3 dx. Remember the derivative of 2 is just 0. And then we need to find our v, that's the integral of e to the 4x dx. Well, that is just 1/4 e to the 4x. And I hope it's getting easier for you to do u substitution in your head. But if not, it'll just come in time, and just take your time and follow the careful methods as you need to. It'll get a little confusing with so many different u's everywhere, so just be careful that you always know which u you're talking about at any given time. Okay, so now we need u times v. Okay, so we have 3x plus 2 divided by 4 times e to the 4x. And then we're going to subtract our integral of v times du. So we have 3/4 e to the 4x dx. Okay, this integral we can do just by use substitution. So now we're going to have 3x plus 2 over 4. So when we do this use substitution, we're going to pull out another 1/4, so we end up with 3/16. Alright, and then we have our e to the 4x because we keep our exponential. And then we add our plus c. Done. Okay, this next one, we have to do this twice. And I want to make sure I have enough room to do this, so I'm going to go to the next page to do this one. So what we're going to do, alright, so our simple function is 4x squared. And our function that doesn't go away is e to the x dx. So u equals du, sorry. So du equals 8x dx. And v, which is our integral of e to the x dx, is just e to the x. Okay, so when we take our integral, then we get u times v, 4x squared e to the x, minus the integral of v du. So that's the integral of 8x e to the x dx. Okay, so this is done. We look at this one. You can't do this one by u substitution. So to do this integral, we have to do integration by parts again. So this time we're going to set u equals to 8x. And this is where it gets confusing because I already had u's and dv's up here. Now I'm going to define new u's and dv's. And our dv, well, actually in this case it's the same thing as before. Okay, so our du is just 8 dx, and this is the same dv we had last time, so our v is e to the x. So we need to plug this back in, and we have, well, we still have our 4x squared e to the x, and then we subtract our u times v, 8x e to the x, minus the integral of v du. So that's 8 e to the x dx. Okay, so we have 4x squared e to the x minus 8x e to the x minus minus cancels plus the integral of this. And e to the x integrals are easy enough, so we just get 8 e to the x, and don't forget your plus c. Alright, so yeah, it can be a little bit confusing because you have two sets of u's and dv's, and you have to be careful with your signs, but it's not too bad. If you have any questions, please make sure to leave comments in the problem solving discussion. And the last aspect of integration we need to cover is definite integrals. And when you're doing definite integrals, this is when it's really appropriate to define your integral as the area under a curve. Because rather than just figuring out which curve this is the slope of, you actually have a starting point and an ending point. And the number you're going to get from your integral is the area under this curve. So the way that you write it when you're doing a definite integral is you still have f of x dx. But now you also write your starting point and your end point. So let's do an example. So let's say we're integrating the function x cubed plus x squared. And we're integrating from x equals 1 to x equals 2. So we do our integral like normal, x to the 4th over 4 plus x cubed over 3. Now there's two different ways you can write how you're doing an integral. You can just put a bar over here and put 1 to 2. But when I have things with multiple terms, I tend to use brackets instead. It's just so I don't forget everything that I have to integrate. So I put brackets around it and write the 1 to 2 right here. And then what we do is first we plug in everything in here. We plug in the 2 for our x's. So we have 2 to the 4th over the 4 plus 2 cubed over 3. And then we subtract, and then we plug in the 1 for x's. So we have 1 to the 4th over 4 plus 1 cubed over 3. So this is another place, because you have minus and some numbers in parentheses, you need to be careful with your signs. So if you work all this out, and I trust you know how to add fractions, you end up with 21/4. Okay, it's fairly straightforward. One thing I would warn you to be careful of is when you're doing u substitution, make sure you don't substitute these numbers in for u's. Make sure you go back to x's and substitute for x's before you plug it in. And that's probably the only really tricky part about doing this. That and watching your signs. So I will give you just a couple to try out. So we're integrating from 0 to 2, the function 2 times e to the x dx. Then we're integrating from 0 to pi over 2, cosine x, plus 4 sine x dx. And the last one, integrate from minus 1 to 2, 3x squared minus 4 dx. So pause the video and work these out. Okay, so when we integrate this, well, this is a really easy integral. It's its own integral to e to the x. We're integrating from 0 to 2. And I'm just writing it with a bar this time because there's only one term, so I'm not going to get mixed up. So we have 2 times e, plug in the 2, minus 2 times e, plug in the 0. So that's 2e squared minus 2. And you can simplify that and pull out the 2 if you want to. Doesn't really matter. Okay, next one. Alright, so if we integrate this, integrating cosine gives us sine. Integrating sine gives us minus cosine. And we're going from 0 to pi over 2. And we are always going to be using radians, unless I say otherwise, and I can't think at the moment why I wouldn't be using radians. Okay, so let's plug that in. So we have the sine of pi over 2 minus 4 times cosine of pi over 2. And then we subtract sine of 0 minus 4 cosine of 0. So you're going to need to know your unit circle. And at the very least, you should have memorized where sine and cosine are 0 and when they are 1. I'll put a link to a unit circle down below. But if you also have the pocketbook of integrals and mathematical formulas, there's also this information in there. So we have at pi over 2, sine is 1. At pi over 2, cosine is 0. At 0, sine is 0. At 0, cosine is 1. Watch your signs. And this comes out to 5. Okay, last one. Okay, we integrate this. We get 3x cubed over 3 minus 4x. Going from minus 1 to 2. Alright, these 3's cancel out. Let's plug in our numbers. So we have 2 cubed minus 4 times 2 minus 1 cubed minus 4 times minus 1. There are a lot of opportunities in here for you to mess up your signs, so make sure to be careful. And I don't really care if you use a calculator to do all this stuff, whatever you like. And I don't care what type of calculator you use either. I mean, don't use a calculator that just does integrals for you. Okay, this comes out to minus 3. Okay, great. Now we are done with integration. Let's move on to differential equations. So you've all shared with me a bit how familiar you are with calculus. Now I'd like for you to leave in the problem-solving discussion. Tell me about your experience with differential equations. How much have you learned about them before? How much do you remember? So what we're doing in this section is we're just going to have a little bit introduction to tell you what differential equations are and just do a little bit of the basics with them. We're going to come back to them later at the end of the semester to use some of the more advanced techniques to solve differential equations. But before we can use some of the more advanced techniques, we need to cover some other material first, earlier in the semester. Okay, so what is a differential equation? Well, the differential equation that you all know is F equals ma. Okay, in this form, it's not a differential equation, but you have to remember that acceleration is the second derivative of position and the first derivative of velocity. So if you have an equation like this and you want to solve for position and velocity, now we have a differential equation. A differential equation is just an equation that has derivatives in it. This is material that corresponds to Chapter 1 in Felder and Felder, your textbook. So if you want to read more about it, I encourage you to go check out your textbook. Since this is a graduate class, I don't tell my students, you have to read this section and this section. I say, this is your resource, it's there for you. Okay, so let's make this look a little bit more like a differential equation that we could work with. Let's think about a spring. You will find, as you take more of my classes, that I have an obsession with springs, just like any physicist. Because springs are where oscillations and vibrations come from, and you can model so many things in nature as springs. And like in lattice structures, in crystals, you have atoms that vibrate. And when you're looking at molecular vibrations, like you have a diatomic molecule, those are going to vibrate. And I cover that sort of thing in my PhD work, so I'm especially obsessed with those. Okay, so in a spring, what's the force from a spring? You should all know Hooke's law. So we have F equals minus kx. So let's plug that into our equation. So we have minus kx equals m d squared x dt squared. All right, so K is your spring constant, that's a constant. M is your mass, that's a constant. X is our independent variable. X is our dependent variable. T, oops, left off a squared. T is our independent variable. So when we solve this, we're going to be looking for something of the form x of t. So when you solve a differential equation, the solution is an equation. So for an example of how that works, I'm going to give you one solution to this equation, and I want you to see for yourself that it works out. So one solution is, all right, capital A here is a constant. It's the amplitude of your vibration. The square root of k over m t. All right, the k over m are in the square root, the t is not. So what I want you to do is plug this into the left side of the equation, which is extremely straightforward because all you have to do is multiply minus k times x. Don't overthink it. Okay, and for the next one, the next thing I want you to do is plug x of t into the right side of the equation. So this is more work because when you plug this in, you have to take the derivative of x twice. You're taking the second derivative of this function. And then you should see that the left side and right side are equal. And this is what it's going to look like when you want to verify that an equation is a solution to a differential equation. So go ahead, work this out, and then press play again when you're done. Okay, I'm going to go over what it looks like when you plug all of these in. So first one, that's easy, just multiply minus k times x of t. Easy peasy. Next one, so we need to find m d squared x dt squared. So I'm just going to write down what x is because I left it on the other page. So we need to take the first derivative of x. So that just pulls out that square root of k over m. And sine goes to cosine. So I'm doing the chain rule here, but I'm not writing out all my steps. Let me know if you want me to write out all my steps. Alright, now I need to take the derivative again. So the square root of k over m is going to come out again. So we get k over m. Okay, and the derivative of cosine is minus sine. Okay, and then we just need to multiply m times that. So that m is going to cancel out with that m, so we're just left with minus ka. Alright, third step was just make sure that this equals this. And they're equal. So that's what it looks like when you found a solution to a differential equation. This is your solution. So your solution is an equation. Now I'm going to give you a couple differential equations and a couple possible solutions, and I want you to figure out which possible solutions are solutions. Okay, so your first differential equation is this, and this is actually the equation for radioactive decay. And your possible solutions are, okay, so in this equation, n is your dependent variable, t is your independent variable, and lambda is a constant. This a and this n naught are also constants. Alright, and the second one I'm going to have you work on. Alright, so this is your differential equation. Y is your dependent variable, x is your independent variable, it's a constant. Alright, so here are the solutions for you to test. So in this one, for each solution you can calculate the left side and the right side and check to see if they're equal. For this one, you just calculate the left side and see if it equals 0. Alright, pause the video and try it out. Okay, I'm going to the next page so that we have plenty of room. Okay, first one. So we need to calculate for A, we need to find what dn dt is. So when I calculate dn dt, when the function is a sine lambda t, I get a lambda cosine lambda t. And when I calculate the right-hand side, which is just minus lambda n, so minus lambda n is just minus lambda a sine lambda t. Okay, these two are not equal, so this is not a solution. Let's try the second one. Okay, when I calculate dn dt, when the function is n naught e to the minus lambda t, I get minus lambda n naught e to the minus lambda t. Okay, now when I calculate minus lambda n, I get minus lambda n not e to the minus lambda t. See, these are equal. So this is a solution. Okay, let's go on to the next one. So this one, well, this one involves a second derivative. So let's find the first derivative of dy dx in this case. So dy dx gives us 3e to the 3x, and d squared y dx squared is 9e to the 3x. And then we have to subtract from that. Well, we'll be subtracting 9y. So what's 9y? 9y is minus 9e to the 3x. So we have 9e to the 3x minus 9e to the 3x. That equals 0. So it's a solution. Hooray. Okay, next one, if we take dy dx, we get 6x. And if we take d squared y dx squared, then we get 6. And when we take minus 9y, we get minus 27x squared. So if we have 6 minus 27x squared, that does not equal 0. So this is not a solution. Okay, so I hope you understand now how to verify if a solution, well, if any possible solution is actually a solution to a differential equation, and that you have some idea of what a differential equation is. We'll come back to how we actually solve for solutions so they're not coming out of thin air. We'll do that next time. But before we do that, I want to talk about initial conditions and boundary conditions. And I will normally abbreviate these because I don't want to write out these words all the time. So this is where you end up you're solving for your solution. You get some general solution, and it has a constant in it, and you need to figure out what those constants are. Let's get a little bit more specific about what I mean here. So let's say we have a differential equation. And just to say a little bit about terminology, this is an ordinary differential equation because there's only one independent variable. It's a first order equation because it only has a first derivative. If it had a second derivative in it, it would be a second order equation. Okay, so this is your differential equation. Let's say you have found a solution. Now the solution is going to be called your general solution because it still has constants in it. And again, we'll get to how we actually get to these next time. Alright, so this is our general solution, y of x. So we have this c, this constant in here. We want to find the particular solution. And that means we have to solve for what c is. Once we find that, we'll plug c back in, and that will be our particular solution. So to do that, we need to use our initial conditions or boundary conditions. And generally, I will use the word initial conditions when our independent variable is time, because we're saying what the conditions are when we start out. And I'll use boundary conditions when we're doing something where we're using variables like x or y as our independent variable, because it's more about the boundaries in space. And when we're doing actual physics problems, and we will get there, it will become a little bit more clear what I mean by that. So let's say in this one that our boundary condition is given that we know that when you plug in 1 for x, the value of this function is 1 over 25. So basically you plug this into here and solve for c. So we say y of 1 equals 1 over c minus 3 times 1 squared. And set that equal to 1 over 25. So we have 1 over c minus 3 equals 1/25. So that tells us that c equals 28. So our actual particular solution is y of x equals 1 over 28 minus 3x squared. Before you have initial conditions or boundary conditions, you really have a family of solutions, all functions of this form. But once you have initial conditions or boundary conditions, you can find your particular solution, which is just one function. Okay, I'll give you a couple to figure out yourself. You're going to be given the general solution, and you're going to be given an initial condition or boundary condition. I want you to find the particular solution. Okay, here's your first one. We're doing radioactive decay again. And I'm just writing your constant as C right now, just to be consistent with my explanation I did a second ago. But it doesn't matter what letter you use for your arbitrary constants. And our initial condition, because remember we're talking about time here, is that at time 0, there are 10 particles. So you want to solve for C and get your particular solution. Second one, your general solution, has a log in it. And I will say that when you're solving differential equations, logs come up all the time. So make sure you're familiar with how to work with logs. Surprisingly, to me at least, the last time I taught this class, the biggest problem my students had with solving differential equations was that they were rusty on how to work with logarithms. Okay, go ahead and find those particular solutions. Okay, so all we have to do is plug in for t equals 0. So at t equals 0, we have c e to the 0, and that equals 10. E to the 0 is 1, c equals 10. So this one has really easy algebra. So your particular solution is n of t equals 10 e to the minus lambda t. And that's why c is called n naught in the way this formula is normally written, because it's the value of n when t equals 0. This next one I would call boundary condition because it's a function of x. Okay, so we need to plug in for x equals 5. So we have 5 squared minus 4 times 5 plus c, and that equals 0. So we have the log of 5 plus c equals 0. That means that 5 plus c equals e to the 0. And this is where you have to know how to work your logarithms, because I am not going to go over that. There's too much else we need to cover. So 5 plus c equals 1, so c equals minus 4. So our particular solution is y of x equals log x squared minus 4x minus 4. Okay, so that's where we're going to stop for today. Next time we will look into initial conditions and boundary conditions when we have a second order differential equation, and we'll also look at one method for how we can find the solution, find the general solution to a differential equation. So let me know how much of this was review for you, how much is new, and put any comments you have in the problem solving discussion. And remember, you need to make that first comment by next Monday at noon. All right, see you next time.